Perfect. Yeah, then thanks again to the organizers for giving me the opportunity to talk at this excellent meeting. I'm going to talk about Einstein-Cartan gravity and implications for Higgs inflation. And so that will tie in very nicely with what Fedor said. Let me just motivate and ask the question, how well do we know gravity? And then you will say, okay, let's write down the Einstein-Hilbert action that I wrote down here. So you see the metric, and then you see the Ricci tensor that is a function of the Christoffel symbols. But this Einstein-Hilbert action does not define the theory uniquely, because as Fedor just said, you have to choose which are your fundamental fields. And then one option that is most commonly used is to choose only the metric as a fundamental field. So that is then the so-called metric formulation. And in this formulation, you assume that the Christoffels are functions of the metric. So a priori, they are just fixed as functions of the metric, and they are fixed in such a way that the covariant derivative of the metric is 0, and that gives the unique Levi-Civita connection. But there's a different choice, and that is the Palatini formulation, where you take both the metric and the connection coefficients as independent fields. And now that seems like a very drastic change of the theory. So what happens if you do that? Well, then, of course, you have to also vary the action with respect to the connection coefficients. And then it turns out, if you take the Einstein-Hilbert action and then perform the variation is proportional to the covariant derivative of the metric. And then, of course, demanding the variation to be 0 again leads to the condition of the vanishing covariant derivative of the metric, and that gives you uniquely the Levi-Civita connection. Even though the formulations are conceptually very different, they are equivalent in pure gravity. Then what happens if you couple to matter? And then throughout I will use the example of a scalar field. So for now, it's just a generic scalar field. Later it will also be the Higgs field. And now let me add to the Einstein-Hilbert action here the matter Lagrangian. And let me assume for now a minimal coupling. So that is, the matter Lagrangian only depends on the scalar field and on the metric, but not on the connection. And then clearly the variation with respect to the connection stays unchanged. And so the equivalence of metric and Palatini persists. But you can change it by the non-minimal coupling that we've seen a lot now. So let me add this term here, where the Higgs field, or the scalar field squared, directly couples to curvature. And then this term comes with a new unknown coefficient psi. And then once I do that, sorry, this looks bad. Once I do that, the variation with respect to the connection changes. And then the different formulations will no longer be equivalent. So that is in the Palatini formulation, the equations of motion for the connection will not give the Levi-Civita connection. And so we see that matter can break the equivalence of the different formulations. And that leads to a very, and this difference of the formulations really has phenomenological implications. So I can just use what Fedor just said. So for example, for Higgs inflation, it really leads to a different tensor to scalar ratio. And so it's really of phenomenological importance which formulation you choose. And so this leads us to the question, which formulation should we use? So since predictions depend on it, it's an important question. But as we've seen, gravity cannot distinguish. So if you only have pure gravity not coupled to matter, then the formulations will be equivalent. And so maybe you can have aesthetic arguments for one or the other, but in the pure theory of gravity, the formulations are equivalent. So it means this choice of formulations, or the choice of independent fields, is really an ambiguity contained in GR. So because if you're in a classical theory of gravity, you say, okay, I have metric GR, then if you don't couple to matter, equivalently you could have used Palatini and would be the same. So it's really an ambiguity contained in GR. now, so from the gravity point of view, you cannot answer the question about the formulation. And so the conservative thing to do is whenever predictions depend on the formulation, one should keep this ambiguity in mind and then explore the predictions for the different formulations that one can choose. And doing so is the goal of my talk. Then I'm going to use the Einstein-Cartan formulation of gravity. Why that? First of all, it contains metric and Palatini formulations as special cases. So by doing Einstein-Cartan, I'm also doing metric and Palatini. As you know, the Einstein-Cartan formulation can be derived as a gauge theory of the Poincare group. So if you take some matter field with a global Poincare invariance and demand it to be local, that is one way of deriving Einstein-Cartan, and that is of course very nice because it puts gravity on the same footing as the other fields of the standard model. And then with the outline of the talk is as follows. I will first briefly review the Palatini formulation and how it differs from the metric formulation. And then I'm going to generalize Palatini to Einstein-Cartan. And there I will just make general statements about the formulations of gravity and how they lead to, like what are their differences. And then in the second part, I will discuss an exemplary application, and namely the application of Higgs inflation. And that will tie in very nicely with previous talks, where I will study the predictions of Higgs inflation in Einstein-Cartan gravity, and then we will see how they are different from metric and Palatini formulations. And finally, I will discuss short applications to other systems. Then for the first part, let me briefly review the metric and Palatini formulations, and I think I can be very fast here after, in particular, Feder already showed that. So I'm again using here the example of the scalar field coupled to gravity. And now I'm writing the scalar field Lagrangian explicitly in terms of the kinetic term and the potential. And then again, the scalar field is coupled non-minimally to curvature. And then the convenient way of analyzing this theory is to perform a conformal transformation of the metric. So let me call this prefactor of the Ricci scalar here omega squared. And then I can rescale my metric as omega to the -2. And then I will see that here the determinant gives me omega to the -4, and the inverse metric gives me omega to the power 2. And so of course, we choose the conformal transformation in such a way that the non-minimal coupling disappears. And then the result is the following. So we have in terms of the new metric, the non-minimal coupling here has disappeared. But in turn, there are factors of omega squared for the kinetic term of the scalar field and for the potential. And here I'm showing the result for the Palatini case. So here I'm assuming that so when I'm assuming that the Christoffel symbols are independent fields, then the conformal transformation does not touch them. And so then I'm getting, so then the transformation only comes from the inverse metric here, but the Ricci tensor stays invariant. And now what happens in the metric case? So in the metric case, the Ricci tensor is also a function of the metric. And so it's sensitive to the conformal transformation. And so in the metric case, I'm getting an additional term here. And now, why is this a convenient way of analyzing? So in terms of the new metric, there's no non-minimal coupling. So in the new metric, the formulations are again equivalent. And so I've mapped the difference of the initial difference of the formulations now to the difference in the kinetic term of the scalar field. And then, of course, one can also redefine the scalar field and map this difference to a different potential in the new metric. So this just is a brief review of metric and Palatini formulations. I think it's well known for many. So now let me go to Einstein-Cartan. So in Palatini, we still assume a priori that the connection coefficients are symmetric in the lower indices. So one can argue there's no good reason to make this assumption. And now, so we can drop the assumption. So just take generic connection coefficients that don't need to be symmetric. And that is how you go from Palatini to Einstein-Cartan, or that's one way of deriving it. So like take the connection coefficients as independent and don't make an assumption about their symmetry. And so this means that we introduce torsion in the theory. So there's an antisymmetric part. In general, there's an antisymmetric part of the connection. And that is torsion. And so that also has a geometric meaning. So if you go along the infinitesimal parallelogram, then how your vector turns tells you how much curvature you have. And then how the parallelogram does not close tells you how much torsion you have. And okay, then let's analyze this theory. Well, let's first say, of course, the torsion that we're introducing here again does not propagate. So there's no kinetic term for the torsion, and of course that is a necessary condition in line with what I've said before. So because if we can call Einstein-Cartan a formulation of gravity, then it should be equivalent to the other formulations like metric and Palatini in the pure gravity case. And then, of course, the necessary condition is that the number of propagating degrees of freedom is the same. So that's not an input; it's just it's a result that I don't. So that the Einstein-Hilbert action does not give me the kinetic terms for torsion. And now the result is even stronger. So if I just take the Einstein-Hilbert action I showed before, and then take don't make an assumption about the symmetry of the connection coefficients, and then vary with respect to the connection coefficients to determine them, it turns out dynamically, so as a result of the equations of motion, that torsion will still be zero, so that the connection is still symmetric. So this means if I take the same action as for Palatini, then I will get equivalence to Palatini. How can we change that? The new feature of the theory with torsion is that I can add additional terms to the action. So for example, here I'm writing the Riemann tensor and I contracted with the Levi-Civita symbol. And then if you assume torsion to vanish, that leads to symmetry properties of the Riemann tensor, and this term is identically zero. But as soon as you drop the assumption about the vanishing of the torsion, this term can give a non-trivial contribution. And so that's called the host term. Yeah. And then for the host term, I can do the same as for the Ricci scalar. I can add a non-minimal coupling. So like I'm sticking to the example of a scalar field here. And then there's another term, the so-called Nian term, that is a total derivative of torsion. And then, of course, as such, it does not contribute to the equations of motion, but I can also add a non-minimal coupling here. And so these non-minimal couplings are on the same footing as the original non-minimal coupling to the Ricci scalar. And then once I add these terms, the equivalence to Palatini is broken. So there will be non-zero torsion in the theory. And it's important to note here that these new terms come with a priori unknown constants. So I'm writing 3 new constants here, and a priori they are not determined. Let's analyze the resulting theory. And so here as an example, I will just use the Nian case. So in the first line, I'm writing the action that I had before. So the Ricci scalar non-minimal coupled to the scalar field, and then the Lagrangian of the scalar field. And in the second line, I'm adding one additional term. So I'm adding a term that contains one additional coupling constant. And that is the non-minimal coupling to the Nian term. And then how can I analyze such a theory? So one method is first to perform the conformal transformation as before to get rid of the non-minimal coupling to curvature. And secondly, I can study the equations of motion for my connection, and then split the connection in a torsion-free part in torsion. And then I can solve for torsion and plug the result back in the action. So I'm not going to show any technicalities here, but just tell you what is the answer. Namely, we can derive an equivalent theory that looks like this. So in this theory, the connection is torsion-free. And then the price we're paying for the torsion freeness is an additional contribution to the to the kinetic term of the scalar field. So the first contribution here comes from the conformal transformation, like in the Palatini case, and then the second term comes from integrating out torsion. So solving for torsion, plugging it back in the original action, and then that gives this additional term. Let's first again take the case xi eta equals 0. So if we don't have the second term here, then in line with what we discussed before, we get back to Palatini. So there's no second term, and we are in Palatini. But there's also an other interesting choice of parameters. Namely, we can just by hand put xi eta equals xi. So xi being the non-minimal coupling to the Ricci scalar. And in that case, we see that this term will be exactly the term that you get in the metric case. And so this shows that we can obtain both Palatini and metric as special cases of Einstein-Cartan. But from this perspective, there's nothing preferred about them. So it's just one special choice of parameters, and I'm not forced to make this choice. Then let me summarize on the first part, on the introduction to Einstein-Cartan. So we obtain it by dropping the assumption of vanishing torsion. So in the Palatini formulation, we put by hand that torsion should vanish. And now we don't do that anymore, and just let the equations of motion decide what is the connection. And then if we take the same action as Palatini, we get the same result as Palatini. But the new feature is that we can add additional terms to the action. These additional terms come with new coupling constants. And then as a method of analysis, we can solve for torsion and derive an equivalent torsion-free theory. And in that theory, maybe let me show that explicitly. So the additional term here, so it's a higher order term. So the term, so the operators themselves have the mass dimension higher than 4. And then of course, there needs to be an inverse energy scale, so there can be a term in the action. And then the inverse energy scale, or this energy scale that divides the term, is always Planck mass divided by the new coupling. And so that's what I'm writing here. The non-minimal couplings in the original torsion full theory translate as an energy scale in the equivalent torsion-free theory. So it's as particular higher order operators. And then we obtain the metric and Palatini formulations as special cases. But from this perspective, there's no reason to choose them. So Palatini formulation, you can maybe say, okay, it's the minimal action, and so there's something special about it. The metric case is just one point in parameter space, and from this perspective, there's absolutely nothing special about that. And yeah, so to my understanding, there's no argument why you should choose this metric point. Okay, that was the first part. What is Einstein-Cartan gravity and what changes? And now let's apply to phenomenology, and let's use the example of Higgs inflation that has been introduced so well in this meeting. Again, I don't need to say much. So from here on, I will think of H, so the scalar field, as the Higgs field in unitary gauge. And then, as has been discussed in great detail, the Higgs field can play the role of an inflaton, provided you add the non-minimal coupling of the Higgs field to the Ricci scalar. And then, as Fedor already discussed, the results depend on the choice of formulation. And so far, only two formulations have been discussed, namely the metric and the Palatini formulation. So most studies of Higgs inflation so far have happened in the metric formulation, but what happens in Palatini is also known. So both metric and Palatini are described by the same action. And so it's again the action that I've been writing throughout. Only difference now that I specialize to the Higgs potential at high energies. So here lambda is the 4-point coupling of the Higgs. And as I said, for Higgs inflation, it's crucial to have the non-minimal coupling psi here of the Higgs field to the Ricci scalar. And then we can use the method of analysis that I showed before, so the conformal transformation. And then depending on metric or Palatini formulation, the conformal transformation leads to a different kinetic term for the scalar field. And then you can define the canonically normalized scalar field and do the standard analysis of inflation. I'm not going to show that here, but just recall the results. So in the metric case, it's well known that matching the amplitude of scalar perturbations gives a psi on the order of 10 to the 3. And so yeah, as was said before, the smallness of the amplitude of scalar perturbations always needs some large parameter in the theory, and so that is the psi. And for the metric case, it's around 10 to the 3. For the Palatini case, the same argument leads to about 10 to the 7. And then let's look at the phenomenological predictions. So I'm showing here the two most important ones, so the scalar spectral index and the tensor to scalar ratio. And then this is a cartoon picture of what the Planck satellite has measured. So the spectral index has been measured quite well. And we have not observed primordial gravitational waves. So we have an upper bound on the tensor to scalar ratio. It's about 0.07 or 0.05. And here I'm using a logarithmic scale for the tensor to scalar ratio to be able to show the Higgs models. And then, as Fedor already said, for the metric case, the prediction for the tensor to scalar ratio is about 10 to the minus 3. And for Palatini, it's about 10 to the minus 10. And so we see that the different formulations of gravity lead to different predictions. Only they have one thing in common here, namely that you won't be able to measure the primordial gravitational waves in any near future. Also, we see that the spectral index is quite similar, and in fact, it's given by the same formula in both theories, so the famous 1 minus 2 over n. And the slight difference I'm showing here comes from the fact that the reheating temperature is different in the two models, and so the number of E-folds before the end of inflation is slightly different. And then, as was discussed, if one can measure the spectral index very well, that can also at some point serve to distinguish the models. Yeah, and so we see metric and Palatini give different predictions, and both are consistent with CMB observations. Okay, that was the review. Now let me go to Einstein-Cartan. And so here for the talk, I'm not going to show the full parameter space, but I'm just going to show the example I already used before. So in the first line, I used the same action that we had for metric and Palatini. And in the second line, I'm adding now the Nian term, that more precisely the Higgs field non-minimally coupled to the Nian term. And now, so to analyze that, I showed the procedure before. It's first making the conformal transformation, and then secondly, splitting the connection in the torsion-free Levi-Civita part and torsion, and then using the equations of motion to solve for torsion. And then one can plug the result back in the action and derive an equivalent torsion-free theory. And this torsion-free theory we can use with the standard machinery of inflation. We discussed before already that as special cases in this theory, we should recover metric and Palatini. So if we remove the additional term, so psi eta equals 0, that should lead to the Palatini formulation. And then one can make this very particular choice of psi eta equals psi. And then we've seen before that this gives equivalence to the metric formulation. But now let's not use any particular choice of parameter. And then what happens is that I have two couplings now, the psi and the psi eta. And of course, the CMB normalization of the scalar perturbations only gives me one constraint. So it means there's one free parameter in the model. So I can express one of the couplings as a function of the other one. And this is here shown in the plot. We have the psi, so the non-minimal coupling to the Ricci scalar on the x-axis, and the psi eta, so the coefficient of the Nian term on the y-axis. And additionally, in color, I'm showing the resulting tensor to scalar ratio. And so now we can identify the different regions. So if the psi is on the order of 10 to the 7, so that's the whole vertical bar here, that is the Palatini case. So psi eta equals 0 is here. And then we see even if psi eta is non-zero as long as it's not too large. We still get equivalence with Palatini. So the psi equals 10 to the 7 and a tensor to scalar ratio of 10 to the minus 10. The metric point should be psi equals psi eta. So we're somewhere here. And so we see metric is just one special point on the curve and nothing particular about it. And then we see that between metric and Palatini, there's a continuous interpolation. And in this continuous interpolation, the tensor to scalar ratio interpolates between the 10 to the minus 3 of metric and the 10 to the minus 10 of Palatini. And so all the values in between become possible. And also there's a region to the left of the metric case here, where you see that the tensor to scalar ratio grows even more. And it even grows to a point somewhere here where it's above the observational bound. And yeah, so we see that so once we go to the Einstein-Cartan formulation, we can write down additional terms in the action. They come with additional coupling constants, and so that gives a great variety of inflationary models. And I've showed you here one example. So let's put it again on the CMB plot. So the gray point was the metric formulation, the black point was the Palatini formulation, and now we see that the tensor to the spectral index stays largely the same, but the tensor to scalar ratio now can be anything between 10 to the minus 10 and 0.1, which is excluded. And also there's of course a very interesting point here, where the tensor to scalar ratio is just below the observational bound. So we see that this is a model of Higgs inflation, where the detection of gravitational waves from inflation is possible in the near future. Of course, it's not. There's nothing special again about this point. So so far I only showed you a very particular point in parameter space where we only add the Nian term. But as I discussed in the beginning, there are the other terms, the host term, and also its non-minimal coupling. And so in our paper, we analyzed the full parameter space. And then the result is that generically inflation is possible. And that also generically inflation is consistent with observations. So for most, with some choice of measure, parameter choices of the additional terms, we see that the spectral index is given by the attractor formula of 1 minus 2 over n. And the tensor to scalar ratio can vary between, so in any value between 0.1 and the 10 to the minus 10. And if you're interested, I can also show you a few more plots on more generic models. But the point now is for Higgs inflation, the predictions are no longer unique. So what was nice with the metric and Palatini model is that it only had one parameter that was fixed by the CMB normalization, and so it gives unique predictions up to questions of what is the high energy value of the Higgs self-coupling. But now this is no longer the case. But at least from my personal point of view, I see no reason to exclude any of the models. So so all of these models are equivalent in pure gravity. And so all a priori are on the same footing. And then from the Einstein-Cartan perspective, there's certainly no reason to choose the metric point. So that's just like a measure zero set in parameter space. And then maybe you can argue for Palatini by saying it's the most minimal action. But even there, as long as there's no exclusion criterion for any model, and I don't know any exclusion criterion here for the Einstein-Cartan formulation, my personal view is that we have to deal with this problem and accept that the predictions are not unique, but depend on the choice of gravity formulation. And so in particular, the tensor to scalar ratio 10 to the minus 3, so the prediction of the metric case, from this perspective, there's nothing special about it. You can go below it, above it, and yeah. Let me briefly give an outlook to other applications. So far I've just discussed the scalar field. And now let me also add fermions to the theory. So here so psi is a fermion, and I'm just writing the just the standard action of a fermion. And then the same thing that happened for the scalar field happens. Sorry?
Sorry.
The same thing that happened for the scalar field happens for the fermion. So we can add additional non-minimal couplings. So these are the two alpha. So these lead to the two parameters alpha and beta. And then if we look at this action, we see that because of the Hermitian conjugate, if you have a torsion-free theory, then alpha and beta, so the terms with the alpha and beta vanish identically. But if you don't exclude torsion, again, these give non-trivial contributions. And then we can do the same story and derive an equivalent torsion-free theory. And then the terms that we get are as follows. So here we have the vector current of fermions. Here we have the axial current of fermions. And then we see that they are vector-vector, vector-axial, and axial-axial interactions. And then they are parameterized by these non-minimal couplings. And again, we see here the energy, typical energy scale is given by the other way. The energy scale is given by Planck mass divided by the new coupling. There's also the special case of the axial interaction. So even if we don't put alpha and beta, there will still be an axial-axial interaction. So that was already derived in the Kibble paper in 61. And then if we have both scalars and fermions, then there will be scalar-scalar interactions. That's the non-trivial kinetic term of the scalar. There are scalar-fermion interactions and fermion-fermion interactions. If you're interested, I can show you the full action. Let me just point to two applications of this field, two further applications. So this fermion, so the four fermion interaction we just saw before, we can use it as a production mechanism for sterile fermions. So because it's a gravitational interaction, so it's fully universal among fermions. And so it's a way of producing from the standard model fermions a sterile fermion in the early universe. And that is a production mechanism for fermionic dark matter. And Inar will talk about this mechanism in the Quarks workshop on dark matter. Also, so far in Palatini formalism, we studied that there exists a gravitational instanton, and that can lead to electroweak symmetry breaking, and that will be discussed by Misha on Monday. Let me conclude. Here I discussed the Einstein-Cartan formulation of gravity. So we saw that it is a generalization of Magic and Palatini, and all the formulations are gravity itself cannot distinguish between the formulations. But once you add matter and appropriate non-minimal couplings, the formulation leads to different predictions. And then one can derive an equivalent torsion-free theory. And this torsion-free theory, the specific higher dimensional operators will appear. So you create the torsion for these specific higher dimensional operators. And then from the perspective of the torsion-free theory, one can say that is a selection criterion for higher dimensional operators. So a geometric selection criterion in the sense of those that can arise from torsion. Such a geometric selection was already used in the study of Higgs inflation. So by writing down the non-minimal coupling in the Jordan frame to derive the Einstein frame potential, one also used this geometric approach. And now from the Einstein-Cartan perspective, it becomes unavoidable to generalize the scenarios of Higgs inflation. So neither Magic nor Palatini so are preferred from this perspective, and it becomes unavoidable to study the more general formulation. And then that is not an advantage in my view, but personally I don't see a way around that. But what is an advantage of this geometric selection of higher dimensional operators are the other phenomena, so the fermion dark matter production and also the generation of the Higgs mass. Thank you very much.
Thank you. Thank you very much. But you don't consider non-metricity, because Palatini usually produce non-metricity as well. You need not.
I mean, if you go from this gauging of the Poincaré, then then naturally you don't have a non-metricity. So because the anti-symmetry of the generators of the Lorentz group kill the non-metricity from this gauging point of view. But I fully agree with you. So from this just dropping assumptions approach, one could also add non-metricity, and I personally don't know a good reason not to. So it's
okay. Questions, please. Other questions? Shravan Kumar, Kumar, please.
Hi, Sebastian. Thanks for the nice talk. Actually, I have a question which is in relation with the previous talk as well. Like, so Fedor explained that adding R square term gives UV completion for Higgs inflation. Okay, here you are generalizing Higgs inflation in the Palatini and torsion framework. So, what do you say about UV completion? Do you still require R square term,
yes.
or you without it you can achieve it?
Yeah, thanks a lot for the question. So there are many interesting things to be said. So first about the UV completion. So as Fedor discussed, in the metric case, the cutoff is Planck over Xi, and this leads to the problem in preheating. So you cannot study preheating perturbatively, and that's why you also, just to have a definite prediction for preheating, you need the UV completion. In Palatini, the situation is better. So the cutoff is Planck over square root of Xi. And so in the Palatini case, the perturbative computation of preheating is possible. So of course you need some UV completion above inflationary scales, but inflation and preheating you can do perturbatively within Palatini. So in Palatini you don't need to worry about the UV completion at this point. And now what you're saying is something that we're studying at the moment in Einstein-Cartan, namely, like, what is the cutoff in the different scenarios? And then that could also provide a selection criterion. So it seems that most models in some measure have the metric-like cutoff behavior, and only a smaller number has the Palatini-like cutoff behavior. And so that could be a criterion to select these Palatini-like models, and also to reduce this arbitrariness introduced in this formulation. So that's the one point about the cutoff. And then second point about the R squared. So the R squared is super interesting because in the metric formulation, as has been discussed, it introduces a new degree of freedom, a new propagating degree of freedom, and that can be used for the recompletion. In the Palatini formulation, the R squared does not introduce a new propagating degree of freedom. So if you study Higgs R squared in the Palatini formulation, you only have one scalar field, the Higgs. And that has also been studied in a number of papers, the Higgs R squared in Palatini. And that is completely different than the metric case because it's only a single field inflation.
Sorry, I'm confused here. I mean, R square model, there is a Palatini version of R square model. So there's no propagating scalar. That's what you're saying? Just say, okay, not mix, it's just pure R square, R plus R square.
That it has the same, it has no additional scalar, no.
You can write a conformal transformation and you can generate.
Yeah, so it's exactly because the conformal transformation generates the kinetic term in the metric case, but it does not generate the kinetic term when the Ricci tensor is invariant.
Yeah, I got it. Well, sorry, I stopped you in the middle. I have a question here. I mean, in the Palatini case, you said the cutoff is MP by square root of psi. But the Xi value is very high in the Palatini.
Yeah, I mean, like in both cases, the potential is the lambda over Xi squared. So in terms, like as a function of Xi, the potential stays the same, but the cutoff becomes higher. But then, of course, you can formulate it the other way around and say in Palatini, the Xi is much higher. And so numerically, the cutoff in metric and Palatini are the same. So it's in both cases something like 10 to the 16 GeV. But because the Xi is much larger in the Palatini case, the numerical value of the potential and correspondingly of the Hubble and the reheating temperature are much lower. And that's why the all relevant scales in Palatini case are below the cutoff.
Okay, next question, Keigo Shimada.
Okay, can you hear me?
Yeah.
Oh, okay, yes, thank you.
Yes.
Thank you for the wonderful talk. I have a question about the scalar and the Higgs and the fermion coupling. And if my memory is correct, in normal Einstein-Cartan theory, without the neon or Hall's term, the torsion does not produce an axial term. And that's why the Higgs, or more like the inflaton and fermions, don't couple. So in your case, the neon and the Hall's terms are the one that actually generated these effective couplings between the fermions and Higgs. Am I correct first?
Yes. So let me go to the slide. So if you take the minimal action, so you don't add any terms beyond Einstein-Hilbert and the minimal coupling of matter, then the only term in the effective torsion-free theory is then the axial squared coupling of the fermions. So that's the only new term, but the other terms, yeah. So I mean, for example, the fermion scalar term always looks something like this. So the d mu h squared times a mu, and then the coefficient of that is something like alpha psi eta. So for such a term to appear, you need both the non-minimal coupling of the fermion and something like the host term or neon term. So yeah, if you take the minimal action, they are not present.
Okay, thank you. So my next question is, you discussed dark matter, but before that, I think reheating in this scenario or model will greatly differ. Am I correct? Like,
yeah, so we didn't study it, and that is an open question. Yeah, so yeah, it will surely be different. I mean, it's just because the kinetic term of the scalar is different, so the Einstein frame potential is different, and then on top of that you have these couplings that I'm showing here examples, so direct coupling of the Higgs to fermions, for example, and that may again change. So yeah, that for sure is something to be done.
And so I suspect it hasn't been done much yet, or are there other groups?
No. I mean, like, so we proposed this theory less than a year ago, and so,
okay.
Yeah. No, I mean, there's the like preheating study in the Palatini case by Rubio and collaborators that Fedor mentioned, but beyond that, I'm not aware of anything.
Okay. And my final small question is, can I see the solution for the connection, please? If you have it in a slide, or
so I only have it in the general case, but that is good enough, I think. So that is the general Jordan frame action we start from, and here we use form language. So I can also say something about that, but so I mean this is the form language version of the Ricci scalar, and then that is the non-minimal coupling to it. And then we have the host term and the non-minimal coupling. We have the neon term here, the usual action for the scalar, and then the action for the fermions. And then we split in torsion-free connection and torsion. And then first we do the conformal transformation, and then this is the result for torsion here. So I mean, it's the torsion 1 form. No, it's a torsion. No, it's a contortion 1 form. So we.
Yes, I'm accustomed. Thank you. Yes, thank you very much.
Okay, so does it
thank you.
Say anything to you? Okay.
And now Alexander Wickman, please.
Thanks, Sebastian. Very nice talk. I don't want to, preclude everybody from going to have coffee, even though there's no way to meet anybody. Well, I have a very simple question. So I'm a bit confused. So if you write basically an action with torsion, it's kind of severely uses the fact that the normal method does not couple to second derivatives, right? But on the other hand, if you start from just, let's say, Einstein equations, and let's say use some imperfect fluid, then imperfect fluid would have viscosity, and that's kind of next order in derivatives, and there you would see that would have torsion there. I think even some derivatives of it, as far as I understand, because there would be explicit second derivatives, and then probably the trick of integrating out the torsion would not work, right? Have you thought about that?
I mean, as long as there are no derivatives, it should work. So if you just have the torsion without derivative in the directly coupled to matter, you should still, I mean, it's still a constraint equation, so it doesn't contain, like, the equations of motion for torsion you can still solve. So in principle, that should work. So also let me comment that you already have the problem for the scalar field. So because, like, I'm writing the action like this, but of course I could also write the action like this, and then replace the normal derivative by the covariant one, and then it's different. So at least in this case, so like here for so what I'm showing here, I think it's equivalent, just a redefinition of the non-minimal couplings. And so I would expect that as long as there are no derivatives on the torsion, that it's a redefinition of the non-minimal couplings. And then, of course, if something produces derivatives, then the theory is completely different.
Yeah, it would be interesting because in some cases, this imperfect fluids play some role, let's say in some like silk dumpling or dumping or whatever. In some cases, one could try to analyze whether it makes any sense. Of course, if one insists that the fundamental action is just normal one, then it's all fine. But for phenomenological application, would be then interesting what arises there.
Yeah. So I mean, if you can send me a reference, that would be great. Just where this is used, and then I can have a look.
Sure.
Thank you.
Thanks.
Okay, the last before coffee, Sergei Sibirikov, please.
Hi, Sebastian. Thank you for the nice talk.
Hi, Sergei.
So I have a question like this. So after you go through, you start from Einstein-Cartan, okay, you go through integrating out torsion and all that, you end up with certain metric theory after all, with some additional higher order operators. Okay, not higher derivative, but higher order operators.
Yeah.
And just from this viewpoint, this don't look very special, these operators.
Yeah.
And this choice naively doesn't appear stable. Like I compute quantum corrections, I will probably generate other operators. So the fact that you get it from Einstein-Cartan, does it imply that actually it is stable somehow, miraculously, or what? What do you think of it?
I think it's a great question. We haven't thought about that. So yeah, it's a great question, and I cannot answer. But just in the broader context of what you're saying, of course, from the metric point of view, it's very peculiar. It's a very peculiar choice of higher order operators. And the whole thing only makes sense if there's some fundamental geometric meaning. So in the sense that this integrating out torsion, we just do for convenience, because we only there are formulas for solving for inflation in the torsion-free geometry, and that's why we do it for technical reasons. But we think of the Jordan frame action, so that the geometry with torsion is fundamental. And then from that point of view, these operators are, so that is a way of selecting these operators. And then, as you say, one could expect that from from the Jordan frame perspective, where you have the torsion-full geometry, that there should be something special about these operators, and they should not generate all kinds of higher order operators.
But have you thought about verifying that by computing loops, say, just yeah, in principle, it could be done by explicit calculation if there are cancellation. I mean, there must be some cancellation then between different contributions.
Yeah, no, we haven't done it, but it's a great suggestion. Thank you for that.
Okay, thanks again.
Yeah, thank you.
Okay, so thanks a lot for everybody who participated in this discussion. And now the next session will be at 6 in 27 minutes.